All right, let's get started. We have some important announcements ahead of time. Don't show up on Monday. You'll be very lonely. No class on Monday, MLK Day. I will be releasing a study guide later today. Hopefully, as soon as I get back to my office. And that will, the way that I work with study guides is I give you a list of topics that we have covered. And some of those topics are in the form of kinds of questions that I would ask, but they're not exam specific questions. They're more like, what is this? How do we use this for that? So the kinds of questions that really get you to think beyond something that is definitional. I don't like anything that is definition, multiple choice, true, false on exams. It will all query a deeper understanding of what we have covered so far in class. Can you apply what we have seen in class to something that maybe you haven't seen before? So it's very likely that on the exam, there will be some method to add to a linked list. It will assume that you have the knowledge of what we have done in the linked list in the back of your mind as you try to implement one of these methods. And if you want to study what kinds of methods those are, I am highly motivated to pull something that has historically been on the 8th, so that we have, when we go over the exam solutions after the exam, we're going through something that might show up on the 8th. So everything that I do in the first 5 weeks of this course has some direct or indirect tie to something that may show up on the 8th. So I'm hoping that by studying for this exam, you are also studying for the 8th. If you're studying for the 8th, you can also, at least somewhat behind the scenes, also be studying for this exam. So you don't have to do both. There should be maximum overlap. You do still get that page of notes. So throw anything you think is useful on that sheet of notes. I'm not going to check what it is. You just have access to that during the exam. My goal in my own exam design is to make that sheet of paper as useless as possible. So the answers won't be directly on it, but you may want to refer to it to get an idea of what was that idea? Oh yeah, that. Okay, now I know what it is. Now I can use it to answer the question that shows up on the exam. What? Week from today. And then we will also have a review class the day before. So next Thursday, we will be spending all day answering questions. And I will come in with no preparation for the day. It will solely be for your questions and going over anything that you are unclear about. So please come prepared with multiple questions. If everyone comes with multiple questions, then we can easily fill up the 50 minutes. If no one comes with any questions, we do a lot of awkward staring at each other for the 50 minutes. Since I have nothing prepared. Yes, I could lecture on new content, but I really don't want to. I want that to be your time to get your questions answered. Questions about the upcoming week? Yeah.
I assume the 8 has to be done on the school computer, not laptop.
Yes. Okay. Yeah, we have VMs set up that don't have access to the internet or have limited access to only things like the Java API. So that you can look up, how do I use this particular Java construct, but you can't query Chat GPT. How do I write this?
Why would anybody try and pull up GPT?
You would be surprised.
Does that mean the what's it called, the IDE isn't gonna be like operating in the middle of the AI?
Right, you have to use IntelliJ on the 8th. Which
I
is,
know, but like IntelliJ, like, you know, has a little bit of AI into it. Is
Ah.
that not gonna work?
yeah, I don't actually know.
If we're gonna do more coding examples in the class, would we be able to do like a day with IntelliJ, so that way we can kind of see?
Yeah. Yeah, we could do something in IntelliJ at some point. Sure. Yeah, we're gonna be doing a little bit more coding when it comes to the sorting that we're gonna be talking about, probably in about a week, a little more than a week. Other questions before we dive back into computational complexity? Yeah.
Is there a head in a circular?
There is. So what I haven't really talked about is the difference between the dummy head and non-dummy head, which is important to know. For the 8th, everything we have done has been a non-dummy head. That just has always made more intuitive sense to me. The only difference is for a dummy head, the head itself, rather than being a reference to the first node that is null when the list is empty, there is always a head object. And that head object has null data. And then the next refers to the first element in the list. So there is always a head. You can always assume that the head exists. You never want to query the head's data, but if you want to get the first element in the list, you query head.next.
So, what is in a circular list that has a dumb?
It has a head. So the way that I would like people to make it is still a non-dummy head. There is still a first element in the list, and it just happens to be that the last element in the list next is the head. The head's previous is the tail. If there's only one element in the list, they point back to each other. But you absolutely can make a circular linked list with a dummy head, where the head's next is the first, and if that's the only node, then that's next and previous points to itself. Questions? All right, let's dive into it. Last time we were talking about all of the different abstract running times. And we ended by talking about, okay, it would be a little bit annoying if we had to make this table of running times based on different input values to try to figure out a regression model for the line or function of best fit to figure out, okay, what is the actual running time of this program? So we were going to transition into analyzing actual code and saying, rather than thinking about this super abstractly, let's at least look at the code itself to find out how fast or slow it is. What is the order of its running time? We looked at the linked list size method as an example of a constant running time for this method, because regardless of the size of the list, what we do with size is we're going to query the field and read the value of the field. You don't have to do any node iteration, query nodes .next to figure out how big it is. If we did have the size field, we didn't have the size field, and we did have to do that iteration, we said it would be linear. Because now as the list grows in size, the amount of time that it will take to iterate over all of those nodes to figure out how large it is proportional to the length of the list, the size of the list. If there are 100 elements, we're going to be querying .next 99 times. If it's a million, we're going to be querying it 999,999 times. It's always the size of the list minus 1. Since we started the head anyway. So we're going to start looking at it. Here is a piece of code. Question I have for you: how readable is that? If you're having trouble reading, there are lots of seats in the front row. So start to get a sense of what this code is doing. And then I'm going to start asking you, all right, how many operations are executed in this code for a linked list of size 1, size 2, size 3, size n? Let's go about this the way I told you we are not going to do this in the long run, but we can start to draw out a table of how many operations there are. Please. So when I say draw out a table, does that make sense? Do people know what that table would contain?
The tally on one side, and then I kind of like your output on the other. So like you go through the code and then.
Yeah, so let's start to think about, okay, this is an assignment. When this code runs, it is always going to run exactly once, regardless of the size of the list. So we do this once. Let's take a look at, we've broken down the for loop's definition into its 3 lines. How frequently is this assignment done? That is the first line of the for. Just once, right? The very first time we run the loop, we do that assignment, and we don't do that assignment every pass through the loop. On the other hand, what about the second line of the for? How many times are we doing that? Once if the size is one, but this is the check whether the loop is over. So every pass through the loop, we have to check, are we done? Are we done? Are we done? So every pass through this loop, this is run once. So now the question is, how many times is this loop run? If you were to analyze this code, is there a way to abstract or think in general, how many times is the loop going to run? Yeah.
Would be n plus one.
N plus one?
Per whole week.
So the node is not null. So now we're looking for. Once we move past the tails dot next. That's now going to point to null, so it will be null. So we're going the element past the tail. Yeah,
The size.
yeah, it's going to be end up being n, the size of the list. So I'm just going to kind of draw this out like that for now. How about node equals node dot get next? How many times does that run? N as well. That's something that we have to do in preparation for the next pass through the loop. Eventually, we're going to prepare for the next pass through the loop that we don't iterate because we're at the element past the tail, which is going to be null. So this is also done n times, where n is the size of the list. Now we're inside of the for loop. How many times are we bumping up our value? N times? Yeah, each pass through the loop, since we know this is going to iterate n times, we're going to be doing this. So this is also happening n times. How many times do we return the tally? Once. So now we're going to say, okay, n is 1, n is 2, n is 3, n is. We're going to go down to n is some arbitrary size. And we're going to try to abstract what we see to be able to make an expression based on this variable, our size. So when n is 1, how many operations are done? 1, 2, 3, 4, 5, 6. When n is 2, how many operations are done? 9. When n is 3, how many operations are done? 12. Abstracting what this pattern would look like if we continued. What does it look like for size? Yeah. Question. So n is 1. If we make a substitution of n for 1, we're going to count how many operations are done here on the right hand side. 1, 2, 3, 4, 5, 6. If n is 2, we're going to make a substitution wherever we see n. That value is 2. 1, 2, 4, 6, 8, 9. That becomes the 9 that is here. Yeah.
Line 4 actually executes once, even if n is 0. Right?
This line,
Yeah.
node is not null. I would argue that's going to be n times. So let's say we have a linked list and we only really need something. Let's say it's size 3. So we're saying node is front, which is the equivalent of our head. So we would have something that is front pointing here. Now we're going to loop and say the node cannot be null. How many times are we going to be checking whether the node is null? So we're going to first check. We're going to go through this logic, bump up the tally. Looping around, we now check node is not null as we move from this node to this node. Then we loop around, we do all of the work. We're going to prepare to loop around again, and if we loop around again, we're going to check, is node not null? It's not null, it's the tail. So we're going to bump up the tally, say node equals node dot get next in preparation for the next pass through, and now node is null, which is false, which means the loop is over. So for a list of size 3, we end up querying node equals node dot get next 3 times. We also end up querying is the node not null 3 times.
But if the size is 0, which is n is 0, it's still gonna run that operation to check.
Yeah, so we could absolutely have an n is 0 case and check that. Usually, if that ends up being a special case, if something happens for that, now we do one thing or we do something that doesn't necessarily align with that. That's not hugely consequential. I like to start with something that is 1, but you could absolutely start with 0. It's just if that ends up being a special case, then you should ignore it.
Why would it not be n+1? Because aren't you querying each of the 3 nodes and then the null reference?
We're actually only doing this when we move from one node to the next, since we started out at the front. The question is, how many transitions are we making? Not how many nodes are we checking? When we transition from here to here, we check. We don't check for the first time, is this node not null? I guess we do, don't we? Let's check if this node is not null, this node is not null, this node is not null, this node is null. So at the n+1. You are right. Say this is +1. It will turn out to be not consequential, but I like to be precise where I can. So if we do that, then this ends up being 7, 10, and 13. So if we wanted to abstract this now down into what is the generic expression based on size, what would this represent? So now instead of having a constant value, we're going to variabilize it. What is the expression based on size? Yeah,
It's on size.
so we want 3 times size plus 1
+1.
plus 4. Yeah, because we have 1, 2, 3, 4 the constant. We have our 3 times our size, wherever we see that, 3 times the size plus 1, 2, 3, 4. I like it. So this will work in general for any value of n that you might care about. So this is one way to come up with a very specific running time for a method, an entire program. You can break it down kind of like this and think about for each line, how many times does that run based on the size of the input, the size of the structure. Once you have some concrete values, you will analyze it and look for the pattern. As that pattern emerges, you will try to abstract from that pattern to say, what is a function that represents how this pattern would grow for an arbitrary input size? There's no guarantee this is linear. This is nice and linear right now because we are working with something that is linear in nature, but we saw lots of different other orders of growth, and we will see lots of different other orders of growth as we study more and more algorithms throughout this course, the following course that is algorithms, but you will start to hopefully be able to appreciate this process. Question? Yeah, yeah. Always feel free to ask that. If I'm doing something that is not what you want, I'm here for you. Please make sure that I don't get rid of that. All right, other questions before this goes away? All right. If you need to refer to it again for some reason, it's on the recording. Hello, future yous. So we did all of that. We did all of this. And we determined that this was linear. 3 times size plus 4, we can make the constant plus 4 go away, that's a lower order. And we can make the 3 times go away because it is a constant multiplier. So this is order n, it is linear. Great. Questions on that conclusion or how we drew that conclusion? Let's do it again. This is a deck constructor making a deck of cards. take a few minutes, go ahead and write out what you think, how many times you think each line is being run. Make a table and see if you can create a function from that table that describes the order of growth of this method. To help you get on the right track. How many input variables are there? Two. So now instead of just considering the length of the list, there are two input variables to consider. What are those input variables? Suits and ranks. So the expression that you end up writing may be based on both the ranks and the suits, because that's something that could scale separately. You could imagine inventing a new card type where there are 6 suits or 28 ranks. Who knows? But thinking about how the scales based on the ranks and the suits, we should variabilize that. Yeah.
Should like one of the first, because one of the first things that stood out to me as being an important thing was the fact that it was a nested folder.
Yes. What happens with a nested for loop?
It is an exponential. Right?
It multiplies.
Or, yeah, it's sorry.
Yeah, for each pass through the outer loop, we're gonna run the entire inner loop. So that tells us everything inside of the inner loop is going to run however many times it runs in that inner loop, times the number of times that it runs, that the outer loop is going to run. Yeah, it's multiplicative.
Would it be appropriate to think of like a nested for the kind of matrix?
Interesting idea. What are you thinking of? Elaborate on that idea.
Well, so you have your initial like for loop, right? Say that's represents n as in like rows, right? And then you have your secondary for loop, which represents n your columns.
Yeah,
Right? So all of your results are going to be n, right?
okay, so you're thinking build some kind of table of how you're thinking of constructing this, where we have each row representing a suit and each column representing a rank.
Yeah.
Yeah, you could absolutely think of it that way. So now, thinking about the outer loop, that's going to run some number of times based on the number of rows that you are making. And then the inner loop is going to run in a way that says for each row, we need to do each column. So I like that way of thinking. Show of thumbs at the moment, how do you feel about the process? I fully expect most people to be about here-ish at this point. So I wanna get a sense of where people are, how they feel about, yeah. So that's about what I would expect. So I'm going to reveal a solution to this, and let's walk through it. There is no shame, we don't have enough practice to feel truly confident about this, but I want to get a sense of how much detail do I want to go into as we start talking about this. So here is a copy of this code with the annotation. When we make the deck, this happens once. This can mostly be ignored. If you're going to make a class, it's always going to happen once. We can just factor that out. It's never going to change the order of what's going on. When we make a new reference variable to an array of 52 elements, that happens once. We don't worry about exactly how expensive that constructor is for the moment. It's one step, it's one assignment, we're going to call it one step. Setting the size to 0 happens once. The initial time through the first for loop, this assignment happens once. We're only ever assigning suit to be something, the initial element, once. However, how many times are we checking whether this suit is less than or equal to the last suit in some enum or list of class constants? It would be the number of those plus 1. We're going to check, just like we said before, we're going to check when it's spades, check when it's, I don't know what comes next. Hearts, checks what comes next. Diamonds, check what comes next. Club, check what comes next. That's outside of the bounds, loop over. So we would do it the number of suits plus 1 times for this check. If we were doing this in a matrix style, it would be the number of rows plus 1. That might be the way that you want to think about it. How many times are we bumping up that suit? S times the number of suits. Now it gets a little bit trickier because we have this inner for loop. So this inner for loop is going to run once for every suit. So everything that in the outer loop would have happened once is going to be happening every time we loop around the outer loop. So we're going to be doing this initialization S times. How many times are we setting rank to ace? We need to set for each of these suits, we need to set to that ace that many times. So we're going to be setting this to the ace of spades, then the ace of hearts, then the ace of diamonds, then the ace of clubs. So we're doing it S times, number of suits times. The check here is going to happen for each suit, but now it also needs to happen for each rank and then plus 1 again, because we're going to check the out of bounds case to know that the loop is over once. So we're going to multiply these together because for each of the inner loop, we're running the outer loop. For each pass through the outer loop, we're running the inner loop that many times. So this is going to end up being S times R plus 1. For each suit, we're going to go through all of the ranks and we have to check if it's out of bounds, when it's out of bounds. So that's how we get that. How many times we bump up the rank? This is now that same S times R. Now we don't have to do that for going out of bounds. It's just the inbounds times. Then how many times are we running or calling this card constructor and setting it to the card? That's going to happen R times F times 12, because it's inside of this for loop that's going to run for each iteration of the for loop, for each iteration of the outer for loop. So again, we multiply. We bump up size, R times S times. Question?
Can we not just substitute in the actual variable or the values for S and R since we're just doing a normal 52 card
We
deck?
want to know how this scales. So we could state that it happens that many times, but it's going to make it look constant. So we want to be able to know how this scales based off of the number of suits, based off of the number of ranks.
So in case we were making some other card deck.
Yeah. Yeah, it gives us more information. We can always make a substitution that says for a standard deck of cards, S is 4 and R is 13. But then we would at least have the information for how this would scale if we wanted to introduce additional ranks or additional suits. Good question. So if we were going to come up with an expression for this, how would we do that? Sum all of these together. What do we get?
You want the actual expression or the process? I think I got 4s plus SR plus 8.
So let's start with the highest order. So the highest order is going to be the RS's.
I missed the RS. The one that-
Yeah, oh, good.
I don't know.
So we have an RS, an RS, an RS, and an R plus 1 times S. So let's factor first. This is RS plus S, might be the easier way to write that out. So how many RS's do we have? 4. We would say this is 4 RS. Plus, how many, we don't have any straight R's, so we can go straight into how many S's do we have? 1, 2, 3, 4. Plus 4S. And then how many constants do we have? We have the 1, 1, 1, 1, 1. Plus 5. So this would be the full expression of the running time of this method. If we wanted to say the order, though, now rather than saying that this is quadratic, we're really just going to leave it as R times S. That is the biggest factor here. As R and S scale, this approaches, this gets less and less important, approaching 0 importance. This gets less and less important and approaches 0 importance. This becomes the dominant term, the dominant factor, and this 4 doesn't matter either. Really. So this is going to be in order R times S, which is really quadratic in some sense. So if you were to ask what order is this, it is quadratic because there are 2 variables that are multiplied together. But in reality, we don't know if one of these is significantly larger than the other. So we leave it as R times S to just let the user know that it scales independently based on, it creates a rectangle with height R width S. Or height S width R might make more sense if you're looking at the rows as suits and the columns as ranks. Questions on that process? So if we were to write out an actual solution, we would say this is in theta RS. That's how I would report that. Yeah,
I might be thinking of something else, but why are we using theta?
because we know the exact order.
Oh.
We will actually learn some new terminology here when we don't necessarily know the exact order, but we know some kind of bound. Yeah.
Well, when you got rid of RS, is that like the same thing you did yesterday, where you just take the.
Yeah.
Exponent?
Yeah, the biggest term. The constants become less and less important as R and S get really big. The S becomes less and less important as the R and the S get really big. So this is the term that's going to tell us the biggest factor, the significantly dominant factor in the running time. As R and S scale really, really big, this term is going to account for 99.99 something percent of the running time. So that's why we state it as such. All right, so let's do it again. Now we're gonna play Go Fish. Now we know exactly how complicated the deck constructor is. So when we see new deck and deck.shuffle, we know how complicated the new deck is. We just wrote an expression for that. Think about shuffling. Instead of just looking at the code, think about how long would that take to do? Don't write out every single line, but even just thinking about the order of what is it going to take to shuffle? However it is that you think about shuffling a deck of cards. How expensive is that? Digitally, to the computer. Question?
I mean, wouldn't the like bigger question be is what our like deck is storing the cards under? Like if it's an array, it's a significantly easier thing to shuffle, say an array than it would be a linked list.
It turns out to not particularly matter. That is an interesting point, and we'll actually talk about it when we go over sorting. Keep that in the back of your mind. Feel free to discuss this with your neighbor. If you're uncertain about something or you think you have an answer, you can verify it with someone sitting next to you. Or behind you, or in front of you.
Make sure that we get no.
If there's no one around you, jump up and down and make some noise.
How do you make sure that?
Yeah, it's a good question. What's a good shuffling algorithm? How are you gonna randomize the order of a deck of cards?
Yeah.
I kept my
Okay.
favorite. I still can't find it.
And we know that take the next element.
Mine will get better.
Whatever location specified in that.
Yeah, that works. Doesn't matter for now. I don't think there's any really better. You have 52 cards. How are we gonna figure out which card is on the bottom of this, on the stack of shuffled cards? We're gonna pick it randomly. Equal chance for each card.
But
Put that there. Deck's smaller. Right. We're going to assume that we're capable of removing numbers in constant time from what we should be looking at. So we're not worrying about resizing the array as we are moving elements to only be in the first 51 positions, the first 50 positions, the first 49 positions. You can do it much more easily with a swap.
that makes sense.
So something like you have a counter at position 0, and then a counter at position whatever the RNG selects. Swap, increment, swap, increment, pick, swap, increment, pick, swap.
I found out, yeah.
We're gonna assume it's all a single operation. It's really a few operations, but we don't have the shuffle code here. What do we think? Do we have an answer?
Is it great?
I like that. It can also be the first half, ADHD 1, me 0.
Yeah. Today.
Yeah. So let's take a look at an answer. So we're gonna define this once, great. We're going to assign once. The deck is going to happen, we said this is in basically order R times S, or R plus 1 times S was the biggest factor that was there. So we can leave this, I'm perfectly okay just leaving this as order R times S for the moment, because we really only care about the order. But if we want to draw out the actual expression here as well, we can. We could write this out as 4RS plus 4S plus 5, if we wanted to. For shuffling, how are we going to shuffle a deck randomly? The algorithm I had in mind was we have an array of 52 elements. We want to randomize the order, so we're going to start at position 0, and we're going to use a random number generator to pick something between 0 and 51, being the index we want to swap this with. So let's say that picks something out here. We're now going to swap these values. So now what is here is random. There's an equal chance that what is here is any particular index in these 52. We're going to bump up the index to here, pick something between 1 and 51. And we're going to swap this position with something else in the unsorted position in the list. And we continue that process until we reach the end. And if we follow that, then what is in every single position at the end of this has an equal probability to be any other card that was there at the end. So what this is doing is we're saying how many operations are we doing for that? Underneath the hood, it's a few more operations than that, but we can just factor it out and say this swap is a single operation. Really going to be a few of those, but since we don't have the source code here, we just can take a guess and say how many times are we going to be swapping values? It is R times S plus 1. We have to know once when we're done. Sure. The more important part is we set things, and then this for loop doesn't happen, even though it's a loop, it doesn't happen a variable number of times. This counter tells us that this runs regardless of the number of cards, the size of the deck. We're dealing 7 cards to each player. That's not variable. Because of how it is coded, this is always 7. If this were a class constant that was something like hand size, now it's a variable that could change. We want to incorporate that into our analysis. But if we're looking at the code, there's no way this 7 can ever change. It's a hard-coded constant. Pretty poor code design. Usually when you see one of these constants, you want to pull it out as a class constant and allow the user to easily make a single change that factors into the rest of your code. But we're looking at this code as it is written. So this happens once, this happens 8 times, 7 times. We see that it's a constant amount here for each aspect of this loop. So unless this is a variable, it is actually constant. So not every loop has to involve a variable. As long as there's a hard-coded constant somewhere that tells you, regardless of this program, this loop always runs the same number of times. Does that make sense? Yeah,
Why does, I less than 7 happen 8 times?
Yeah,
Zero to
that's a good question. Let's figure this out. So I'm gonna set a value for I, and I'm just gonna kind of count it down here. So I is 0. The first time we ask, is 0 less than 7? So that's one instance. We ask, is 1 less than 7? We ask, is 2 less than 7? That's true. Is 3 less than 7? Is 4 less than 7? Is 5 less than 7? Is 6 less than 7? Is 7 less than 7? This is the first time that it's false, so loop over. How many times did we ask the question? 1, 2, 3, 4, 5, 6, 7, 8. 8 times. Pretty inconsequential in the big picture. If we're going to figure out the order of this, that mistake wouldn't change your answer. So because of that, I'm not hugely concerned with something like an off by 1 error, unless it would change the order of your answer. Then you should know it, and you should be able to identify that this changed. So what expression do we get? Other questions?
Can you
Yeah.
talk a little bit more? I don't know, we don't have a lot of time, but RS plus 1.
This RS plus 1?
Yeah, I don't really get how you got the expression.
Yeah, so this is just the number of swaps that we need to do before we determine no more swaps need to be done. This honestly could be RS, because we could do it up until we reach the last one. So we're gonna swap position 0 with something. We're gonna swap position 1 with something. We're gonna swap position 2 with something. How many positions are there in the array?
It's
Rank times 2. Yeah, R times S. Once we do that, we reach all the way at the end and we swap the last element with something between itself. So we're gonna swap it with itself. You could argue that we don't really need to do that. We could say it's less than that value. By the time we get there, we're over, in which case RS would be a perfectly valid number to have here. But depending on how you do it, you might want to choose to swap that last element with itself. If you do, this is gonna happen an extra time.
We're assuming we don't know how many ranks it suits.
Right, yeah, so this array is gonna be of size R times S, whatever that happens to be, and that's inherent in our deck constructor. Because there was some rank and suit variable in there that we could go modify, and that would change the size of the array that we made.
Right.
Although if we actually look at the code that was there, I think it hard coded the 52.
Yes.
Yeah, maybe I'm still, yeah.
The better solution to that would be to make it rank dot size times suit dot size. So we add all this up, we get an expression. Yeah,
We need to add all the steps or how many times if before initialization would be in one line. So is I the 0, I was.
so here.
Yeah.
Yeah, so we're doing the initialization once. But then how many times are we checking whether that variable is less than 7? That was gonna be 8 times. We have to check it for 0 and 1 and 2 and 3 and 4. It's the equivalent of a while loop. Inside of that, we go back and check the condition each time. So a for loop works exactly that same way with this middle segment. The initialization is the equivalent of something like. This happens once. This happens some number of times based on the number of times this loop is going to run. And then everything that happens inside of here is going to be the number of times. You can imagine that this is some other stuff, and eventually there's a, I++, something that prepares you for the pass through to eventually make the condition false. So this 1 NN is very frequently when you see a for loop. This first step refers to that line, the second step refers to this line, and the third step refers to whatever we do inside of that loop in preparation for the next pass. And then everything inside of the for is everything else that's inside of the line. Does that make sense to everyone else, how this is equivalent or how it's related? All right, well, we're basically out of time already. That flew by. Probably less so from your perspective. But we'll come back to this on Tuesday and try to finish up. Get a bigger sense of What happens when we don't know the exact order of something? How can we bound things? How can we come up with a new kind of terminology when we know it's at least this or faster? It's at least this or slower. I'll leave that in your mind. Have a good long weekend.